In this example, we're asked to look at a two-member truss that's shown here. We have the truss pinned to ground at A and B. We have a load P, which is acting at joint C. What we want to know is that what's the resulting axial stresses in members 1 and 2, and secondly, what's the horizontal and vertical components of displacement for joint C. That is, we're looking for UC and BC. Before we start, what I would like to do is define some angles in our truss. The first one here is going to be the angle of alpha. The second one is the angle of beta. Where from the figure we see that the angle alpha is the inverse tan of the opposite side of that right triangle, which is H, divided by the adjacent side, which is B. Same way for beta. That's going to be the inverse tan of the opposite, which is 2H, and the adjacent side, which is 3B. Also going to define an additional set of angles which we'll use later on in our displacement analysis, and that's going to be the angle of theta 1. It's the same as the angle of alpha. And theta 2, the angle for length 2, is nothing other than the supplement of the angle of beta, 180 minus a beta. We'll talk about why they're defined like that in just a bit once we get to that point. Okay, so the first thing we need to do is draw an FBD. I'm going to draw a free body diagram here of joint C. And keep in mind that what we have are these links that go from C to A, from C to B. So these define the lines of action of some forces here. Again, let me make sure that I'm clear on this. This is A, and this is C, and this is B. So the force that I'm going to draw in first here is going to be the load that's carried by member 1. That's called F1. And then the load that's carried by member 2 is along the line CB. That's F2. And to repeat the angles that we have drawn above, this is going to be the angle of beta, defined above. This is going to be the angle of alpha, defined above. We have the applied force P. It is at an angle of phi, which is given in the problem. So I think I've got everything that I need here. Yes, except I do need to tell us what we're going to use here for X and Y. So from this one FBD, this is of joint C, we're going to write down our two equilibrium equations, summation of forces in X and Y. So this is again for joint C. Summing forces in X. What I have here is minus F1 cosine alpha plus F2 cosine beta plus our applied force P. That sum is a 0 for equilibrium. That's going to be our equation 1. Equation 2 is going to be summing forces in Y. So that's minus F1 sine alpha minus F2 sine beta plus P times sine of phi. It looks like I goofed on my first equilibrium equation. This should be P cosine of phi to get the right X component. So those are our first two equations. We have two equations. We have two unknowns, so this is a determinant. So this means that we can solve for these. So what I'm going to do is multiply equation 1 by sine beta. I'm going to multiply 2 by cosine beta. And in the end, I'll take those two resulting equations and add these. The reason for this is that gets rid of the F2. When I add these two after doing those multiplications, they will cancel out. What we're left with is going to be minus F1 times the quantity cosine alpha sine beta plus sine alpha cosine beta. And then we have P times cosine phi sine beta plus sine phi cosine beta. And just so I don't have to write down a lot of these terms so many times here, I'm going to use a trig relationship that reduces that sum back to sine of phi plus beta, and use the same trig identity here, and this becomes sine of phi plus alpha. So what this means is F1, the load carried in member 1, we get as a plus sign times sine of phi plus beta divided by sine of phi plus alpha times P. And being that we got a plus sign, I assume that they were in tension from the beginning. The plus sign means my assumption was correct. So therefore, member 1 is in tension. If I take equation 1, now in order to get an equation for F2, this becomes F2 is equal to F1 cosine alpha minus P cosine phi divided by cosine beta. And I substitute in the numbers, or the expressions I should say there for F1. I get sine of phi plus beta, sine of phi plus alpha minus cosine phi divided by cosine beta. We can't really tell just by looking at the symbols here whether it's in tension or in compression, so the word here is we need to plug in numbers to determine if it's in tension or in compression. It's going to depend on the angles that we have in our truss. So from this, we were able to solve for F1 and F2. For part A, we have then the stress in member 1 is F1, the number we get back from that, divided by the cross-sectional area A1. So we have a number for that. The stress in member 2 is the load carried by that member divided by the cross-sectional area A2. At this point, we have everything that we need, so that we're going to end up with a number there on the right-hand side. Part B, we're asked to eventually find the displacements there for joint C. So the first thing I'm going to do is find the elongations. The elongations in member 1, the standard equation here is F1 L1 divided by E1 A1. So the length of member 1 is the square root of h squared plus b squared. The material is the same in all or both lengths, so we're going to write that E same way with the cross-sectional area there of A. The elongation in 2, that's going to be F2 L2 divided by E2 A2. The length of member 2, that's 2h squared plus 3b squared divided by EA. So that gives us our elongation. In order to get displacements out of there, we need to be able to relate elongations back to displacements. We're going to use our elongation displacement equations here of E1 is equal to the displacement of joint C cosine of theta 1 plus VC sine theta 1. E2 is UC cosine theta 2 plus VC sine theta 2. And this is where what we did before at the beginning talking about the angles is a useful thing. So from the figure we have that theta 1 and the angle alpha are the same. Theta 2 we said was the supplement of beta, like this. So keep in mind that these two angles are very specifically defined as being the angle from the positive x direction measured counterclockwise at the base of each member to it. So it's probably a little worth going back and looking at the picture. Okay, so if we go to the base of 1, that's here at A, we draw a horizontal line in the positive x direction. So theta 1 is measured counterclockwise there at the base. Same way here for member 2. We go back to its base point there is B. We measure from the positive x direction in a counterclockwise sense and theta 2. Very specifically it has to be that in order to use those compatibility equations that I wrote down here. The point being is that this here is a known amount, E1. We found that above. So these are known, and therefore E1 and E2 are. So what we have here are two equations and two unknowns, and I'll just simply say here we will solve these two equations for UC and VC. So in this problem, we were looking at a truss that was determinate. So by looking at it as a rigid body and all the components as a rigid body, we were able to extract the loads that's carried by each member in the truss. From that, we used our elongation equations to find the elongation of each one, and then using the compatibility equations, we were able to solve for the displacement of that node there of C. Had the problem been indeterminate, we would still have the same steps, except we would have to solve all these equations simultaneously rather than the sequential way that we did here.